Okay, let's continue on to part 2 of our analysis, and this is where we're going to do our multiple regression analysis. So we're going to come up here, we're going to go into Data Analyst, and it's going to pop up all these different wonderful kind of data analysis equations that we can run. And so what we're going to look for is regression. We'll hit OK, and we're going to bring up our box. Now, there's going to be a lot of information in here. So let's start taking a look at it. So the first thing is input y range. This is going to be the y variable on our regression equation. So usually this is what we're all calculating to. In this case, it's going to be the total cost. It is the dependent variable because it's dependent on the other variables. Our x range, those are going to be our x variables, which we can have more than one. And so our x range are going to be the dependent variables. Sorry, the independent variables, because they are independent of anything. The dependent variable is the y-axis. Got a couple different options here. We can set confidence levels constant 0, da 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 da. The important one is labels. We're usually going to use that because we want our things, we want to grab our labels at the top of our rows because we actually want our coefficients to be labeled what the units are. Especially as we have bigger and bigger multiple regression equations, this is going to make our life a little bit easier. We can plot some other stuff. We can look at residuals and whatnot. We're not going to really do that because we want to just, we're going to analyze it on our own. So input y range, we're going to select the y range including the title because we checked that our data has labels. And then for the x range, we're going to select all that. Now this is why you're going to want your y values separate from your x. You want all your x values together. Depending on the problem, if we have to do data cleanup, typically what I'll do is I'll move the cost over and have the y variable in the very first row, and then all the other rows being the x variable. In this case, it's pretty simple, so we're just going to leave it with that. And then output range. We can have it a new workbook, a new worksheet. We're actually going to put it right on the page, and I'm going to say just drop it right here. And this is going to drop down all of our data from the calculation. And then I'm going to hit OK, and it's going to run our regression analysis. And so as we sit here, we've got a lot of data. Let's talk about it. So let's start diving into this data and figuring out what it means. I'm going to just make a couple of these cells, make these all fit to the width, so that way we can make it easier to see what is going on. And we are going to be looking at the first and the third box mostly. But we'll talk about the other box also. Now, if we're going to look at this from the aspect or from the lens, using the lens of hypothesis testing, our null hypothesis is going to be there is no linear relationship between the variables, between y and x. And so our alternate hypothesis is going to be there is a linear relationship between y and at least one x variable. So we are going to be testing whether or not there is a relationship between them, and our test statistic is going to be the p-value. So that's what we're going to be checking on these. P-value. So let's start working through all of this stuff and seeing what it means. First of all, multiple R. Multiple R is our correlation coefficient. So remember, this tells us how well the data correlates with other data. And so this is going to be a -1 to 1. Now, this is multiple R, so we're talking about a correlation between all of the data that we've got. Now, so R squared is interesting. So R squared is typically what we're going to look at the most. And what this is we've got a percentage there, so 94.5. So, and actually rounded to be 94.6. Now, if I look at this, let's just, I want to get this stuff out of the way. We'll move this over here. So if I look at this, an interpretation of this value means that 94.6% of the variation in Y, which is our, in this case, our total production, can be explained by X. So that means the 94.6% of the variation in the total cost can be explained by how many units A, B, and C that we make. This is good. Obviously, this is a key number. And this is actually a really good value for it. So, you know, upper 90 is fantastic. Adjusted R squared is another method of dealing with stuff. We're not going to worry so much about that one. Standard error, and remember we've talked about standard error with a bunch of other things. Just as a number that you want to be low is the one thing that you need to keep in mind for it. Typically, regression statistics, that's the one that we're really going to key into is the R squared. So ANOVA is something that we will not be doing much of in this class at all. But just so you know, what is ANOVA? It's analysis of the variance. And so as we look at it, here's our regression, degrees of freedom. SS is the sum of the squared. MS is the mean squared. And then we've got F. I can't, off the top of my head, I don't remember exactly what F is. So as we're looking at the residuals, that's what's left over. That's not what we're going to be looking at. But the goal for this number is to minimize this number to get the least squared line. So and once again, I got to move this again. It kind of gets in the way. So once again, ANOVA, we're not really going to be looking at the ANOVA. So now we get to the last part, and that's our coefficients and all of our variables that we have. So this is the variables for the regression equation. That's our intercept and our coefficients for A, B, and C. So we can build the regression equation based off of that. But what we need to do first is we have to go look and see, because these are the slope values for each of our variables. The intercept is always going to be there because it is a linear line, but these are our slopes for different variables. So now what we want to do is we want to test our hypothesis. And so our hypothesis says there's, you know, the null hypothesis is there's no linear relationship between any of these x variables and y. So if I look at the first one, the slope is not equal to 0. Because if there was a no linear relationship, the first test would be HO, the null hypothesis, the slope is equal to 0. The alternate hypothesis then would be if the slope of this variable is not equal to 0, and I guess we'll use that as is not equal to 0, there is a linear relationship between this variable and y. Okay. So right now, as I look at it, all of these reject the null hypothesis because it appears that there is a linear relationship between that variable and y. Now, the problem is we need to look to see if the relationship between that variable and y is significant enough to keep in our model. And so how we're going to do that is we're going to look at our p-values. And this is going to be the test to tell us whether or not the value, the variable adds value to the model. So if the p-value is less than 0.5, so that 5% interval, then there is a relationship. The variable should be kept in the model. So if the p-value is greater than 0.5, then there is no relationship, and the variable should be removed. It's almost like a two-pass filter, because if this is 0, that would be showing that there is no relationship. But the problem is we have multiple variables, multiple little guys going in here, so we don't want to go based off the coefficient, because we may have a coefficient in here that is not really useful to the model, that's mucking up the coefficients. So what we're going to do is, to test the hypothesis, we are going to use this p-value to find out if they're significant. Now, in this case, I look at all these. Now, mind you, we never look at the p-value for the intercept, because the p-value for the intercept doesn't matter, because the intercept, there is no statistical correlations that we need to worry about. The intercept is the intercept. And so what do we do? Well, if all the p-values are less than 0.5, we can keep all the variables and continue the analysis. You can hear it now. Dr. Camp, what do we do if one of the variables is not less than 0.5? We start removing variables from the regression equation, the regression analysis, and then we rerun the analysis. So what you do is you pick whichever p-value is the largest, you remove that one first. Even if there's multiple ones, you remove that one first and you rerun it, because that might make the other ones significant. Okay, and so then we just keep going. Now this is, you'll notice these are just raw numbers. So if we remove a variable, we'd have to rerun the analysis. And typically what I tell people is, what you would do is you'd keep this one, you'd copy the data tab, you'd remove the line, you'd rerun the analysis. And you'd rerun it just using the data analysis pack. Okay, and so that's how we test our hypotheses to find out that if any of these that shouldn't be there. And once we're to the point where we keep all the variables, then we continue our analysis. And we'll be continuing that in the next video. If you have any questions, please let me know. Otherwise, I'll see you at the next video.